All right, good morning, everybody. This is the video 2 where we're going to go through and review some trigonometric ideas, so some stuff from geometry, maybe algebra 2, depending on how much you looked at in that previous course. We're going to build on that by looking at some new ratios and then by looking at some special right triangles and how those ratios play a role. Now, what I'm going to do with this video is, because these are my 3 goals, this video is going to be kind of broken down into 3 separate sections. So feel free to skip ahead, go back to what you need to. I will, if I can get a little bit more advanced, I will try to set in there that and try to kind of put in markers so you can find where you need to go for what you need to review. Okay, so this first part is going to be on reviewing right triangles. And specifically some important relationships in right triangles when we look at them. So just to kind of start, I'm just going to kind of draw a basic right triangle here. Here's my right angle. When I have a right triangle like this, the 2 sides that are creating the right angle are called legs. The side across from the right angle is called the hypotenuse. And this is true no matter what right triangle you're looking at. Notice which side you call the leg doesn't really matter. It's the hypotenuse that's always defined. So when you're looking at a right triangle, try to always locate that first, because in our formulas and our ratios, that h is very, very unique and very special. So make sure that you are paying close attention to where your hypotenuse is. Now, one of the kind of key features here is that in a right triangle, one angle is very unique in that it's 90 degrees, and then it's the other 2 angles that can be really anything. You have some flexibility here. Now, what's true though is if I focused on this angle here, my angle of theta, it's got to be greater than 0 if I'm going to create a triangle, right? It can't be 0 because then I would just have a line. But theta also maxes out at a specific value. And I'm kind of curious to see what you think that max value is. So just kind of give you a second to try and guess. Well, the maximum value that this angle can be would be 90. And it can't be 90 degrees because if this angle here is 90, then we would create an open box. It's not a triangle. But the second that that angle is a little bit less, then I can now create a right triangle by going through it. Just be very, very, very steep. Now, the second that we clarify and we start focusing on a specific angle, I can actually be a little bit more specific to which legs we're looking at and which side I'm talking about. Because if I just said look at the leg, you wouldn't know which one I was talking about. All right, so what I can do is, if that is my angle, then this leg becomes the adjacent, since it's the leg that's right next to the angle I'm looking at, and the other one becomes the opposite, because it's literally the leg opposite of my angle if I go straight across. Again, hypotenuse is always hypotenuse. And so we have these 3 sides to a right triangle, specifically if my angle is right here in the lower left. If my angle was up here in the top right, then notice my classifications would have to swap. Then this side becomes the adjacent. This side would become the opposite when looking at it. So notice that this terminology, again, really depends on which of the 2 other angles we're looking at. And I've already honestly taken this video once where I keep forgetting to put the angle in. So I'm going to try to do my best to not forget that as we go through. Now, I'm just going to kind of clean up my triangle a little bit. What I'm going to do is this side here, I'm just going to let this be represented by an H. The opposite, I'm just going to let be represented by an O, and the adjacent be represented by an A. Because what I want to start looking at, and this is where mathematicians and philosophers who really like to think and ask questions and look at relationships, they really wanted to start looking at, okay, well, as my angle is changing, um, what happens between sides of a right triangle? And we have three different sides, so they wanted to focus on just pairs of sides. And they specifically wanted to compare these two things. Well, when I'm comparing two quantities, we call that a ratio. Two quantities. In mathematics, we call this a ratio. So what I'm about to show you is what's called the trigonometric ratios. It is the names given to specific pairs of a right triangle given a specific angle. The first one is called sine. It is abbreviated by SIN. And when you want to find sine of a specific angle, you are taking the opposite side and dividing it by the hypotenuse. And so it's looking at specifically the relationship between those two sides for specific angles. The second one is called cosine. It is abbreviated as COS, cos. And it is specifically the ratio, the relationship between the adjacent leg and the hypotenuse of your right triangle. Tangent is the final of the big three. It is abbreviated as tan, T-A-N, of my angle. And this is the relationship between the opposite leg and the adjacent leg. You've been taught, and we kind of look at this, we just say O over H, A over H, and O over A. To help memorize this, you've learned different acronyms. The most famous one that has been taught for years and years and years is SOHCAHTOA. So sine, opposite over hypotenuse, cosine, adjacent over hypotenuse, and tangent, opposite over adjacent. I was actually taught in my geometry class another way. This teacher was pretty wild, and ended up getting fired after this first year. She wasn't a great teacher. She didn't really click with our class that much. But she did teach me this one thing, and I've never forgotten it since. And I've always taught it this way and tutored people in this way. But I've always learned to keep this memorized by saying some old hippie caught another hippie tripping on acid. And so it's just funny. And so you can kind of see SOH, there's my so, caught another hippie, there's my ka, and then tripping on acid is my toa. And so it's just a way to kind of help memorize what ratio goes with which trig, sine, opposite over hypotenuse, cosine, etc., all the way through to tangent. And so just to kind of give an example, let's say we had a right triangle that was, I'm just going to kind of draw an arbitrary one. And let's call this a 3, 4, 5. Triangles that are 3, 4, 5 are when a right triangle has sides that are whole numbers like this. This is called a Pythagorean triplet. There are unique numbers. I just spelled that with 2 T's, but that's okay. There are unique numbers like this where there are 3 numbers that form a perfect right triangle in your construction. Another one that's very common is 5, 12, and 13. I think another one is like 7, 15, and 16. There's another one that deals with in the 20s, I think. But feel free to kind of look those up. They can be useful, but most of the problems you'll kind of see these. And so what a problem would look like is I would say, okay, given this right triangle and given theta in the lower left, determine the trig ratios for sine cosine, and tangent. And so we would go through and say, okay, well, sine of my angle, what is cosine of my angle, and what is tangent of my angle. And we can use SOHCAHTOA, we can use the Some Old Hippie. However, we need to go through and do this. So I'm just going to pause for a minute. Feel free to pause the video, and then I'll continue working. Okay, so to find sine, I know that this is going to be opposite over hypotenuse. So because my angle is here, opposite is 3, hypotenuse is 5. So sine is literally 3 over 5. Cosine is adjacent over hypotenuse. So the adjacent is 4, hypotenuse is 5. Tangent is opposite over adjacent. So this would be 3 over 4. And that's it. Sine is literally this ratio. It's literally this fraction. Cosine is literally this fraction. Tangent is literally this fraction. You don't write tangent over again. Notice how it's just written once. Same for cosine and sine. When you're finding sine, cosine, and tangent, your answers are numbers. Your answers are these fractions. And that's our target and that's our goal. I've seen in the past a lot of students always want to keep writing sine or keep writing cosine, but just be careful. It's not, right? These is literally telling you to find the ratio, find the fraction here between them. And so this is just kind of your review for your trigonometric ratios for right triangles, and is the end of our first kind of target. And so the next part is going to dig into the new ratios. So feel free if you want to move and practice this if you need it, or skip ahead to the next section, you can. Okay, so now our focus is going to be on learning the remaining new ratios for a right triangle. As you see, I've got listed sine, cosine, and tangent. These are the big three that we just got done reviewing in the first part. And so in the second part, we're going to learn about the other three. So there are 3 new ones. So I'll kind of put that here, ratios. And it's kind of not fair to say that they're necessarily 3 new ones because they're not just completely different things. Remember that the ratios are comparing 2 sides of a triangle, and the big 3 already relate the pairs together. It's really just in the order that they compare. So for example, notice that hypotenuse never appears on top, right? If I focus right here on sine, it's the relationship of adjacent to hypotenuse. Well, what if I want to do opposite to hypotenuse? Well, what if I want to do hypotenuse to opposite? Well, we can do that, but it's not called sine anymore. What that is called is cosecant, which is abbreviated as CSC. And its ratio is relating that hypotenuse to opposite. If I have cosine, which is adjacent to hypotenuse, if I want to look at the flip of that, then what I'm looking at is called secant, which is abbreviated as SEC of my angle, and that is hypotenuse over adjacent. Tangent, if I want to relate this the other way, and instead of doing opposite over adjacent, I want to do adjacent over opposite, this is called cotangent, and that's abbreviated as COT of my angle. And this is now adjacent over opposite. So notice that in these new 3 ratios, what I'm really doing is I'm just looking at the flip of the big 3. This is known again as the reciprocal or reciprocating a fraction or a ratio. And so another way to kind of look at these big 3 is they call these the reciprocals. And we'll give this a specific name later on when we're talking about formulas. But when a question now is asking for to determine all 6 trig ratios for a right triangle, I want to see all 6. I want to see sine, cosine, tangent, and I want to see cosecant, secant, and cotangent. And so I want to give you a second example to do that with. So here's example 2. Again, this triangle is not going to be drawn to scale, and it's going to be a little bit more difficult, just to kind of up the ante a little bit. And the way that I'm going to kind of do that is I'm going to say that this side here is 3, the hypotenuse is 4, and then I'm also going to put my angle here in the upper right. So I want to determine all 6 trig ratios for theta given in this right triangle. And so I want to find sine of my angle, cosine of my angle, tangent of my angle. But not only do I want to find that, I also want to find cosecant, secant, and cotangent for this specific triangle. And one thing that you'll probably notice right off the bat is that this triangle is missing one of the legs. I'm missing specifically the opposite side here. And that's really important because then how am I going to find sine, right? How am I going to find cosecant? How will I find tangent? How will I find cotangent if I don't know this side? And so your first task, if you were to think about this in terms of steps, is to find that missing side. So find whatever is not there. And so how do I find the missing side? Well, that involves Pythagorean theorem. A very, very important theorem, one that hopefully you have memorized at this point. And it is a squared plus b squared is equal to c squared. C is always the hypotenuse. That's probably the biggest thing to remember. And this theorem itself is going to pop up a ton for the remaining weeks in this class, all the way even into the beginning of the next mod. And so it's something that's going to be very, very, very important to be able to use and be comfortable with. And so try to solve for the missing side here. I'm going to pause for a second. Feel free to pause the video. And then I'm going to go through and find the missing side and then find my ratios. Also pointing out one other thing we have to do algebraically, and that you'll see. Okay, so I'm going to go through and do the Pythagorean now to try and find the missing side. Now A and B, because these are the legs, it doesn't matter which side is A or B. I'll just let the missing side be A. That means B is going to be 3. And C has to be 4. So I have A squared, 3 squared is 9, 4 squared is 16. I'm going to subtract the 9 over, so 16 minus 9 is 7. And then I'm going to take a square root, so I get A is root 7. And so that's what my missing side is. So this opposite side right here is root 7. So now that I have now that I have all 3 sides, I can now go through and find all 6 trig ratios. Sine is opposite over hypotenuse, so opposite over hypotenuse. So that's root 7 over 4. Cosine, caught another hippie, is adjacent over hypotenuse. So this will be 3 over 4. And then tangent is opposite over adjacent. So in this case, root 7 over 3. And so here's the big 3, very, very similar to the previous example. The hardest part to this, the extension to it, and the newer part is to now find these other 3. Now what's really nice about these 3 is that in our definition for them, notice that we defined cosecant as hypotenuse over opposite. I don't really have to go through and do that. Now I can, right? Cosecant is hypotenuse, so that's going to be 4 over opposite, which is root 7. So that's 4 over root 7. But notice how that's really just taking sine and flipping it, because again, that's what they are, right? These other 3 trig ratios here are just the flips. They're the reciprocals. So I don't really need to go back to the triangle once I have the original 3. All I need to do is take these answers and literally flip them. Secant would then be 4 over 3. Cotangent would be 3 over root 7. They're the reciprocals. And so this would be all 6. For now, these are the final answers. So root 7 over 4, 3 over 4, root 7 over 3, 4 over root 7, 4 over 3, and 3 over root 7. Now, some of you may recognize this, and it's okay if you didn't, but my answers here cause some problems. The 4 over root 7 and the 3 over root 7. And the problem is I can't divide by a square root. And the reason is a square root, it's not a rational number, right? It's irrational. Root 7 is a decimal that never terminates. So there's no way to actually divide by root 7. And because that's what this expression is saying, I want to change it or manipulate just what it looks like to get away from that division by root 7. And so to do that, to fix this, I want to do what's called rationalizing the denominator. And so to rationalize, I'm going to multiply top and bottom by whatever my square root is, whatever it is. So for cosecant, if I have 4 over root 7, I'm going to multiply this top and bottom by radical 7. When I multiply up top, I'm just going to multiply 4 times root 7, so that's just literally 4 root 7, over, when I'm multiplying with these square roots, we multiply outsides together, so 1 times 1, and insides together, 7 times 7. So I would get root 49. And then now I'm going to simplify. Well, up top I can't do anything, but the square root of 49 is 7. This is my final answer. This is rationalized. So cosecant, I can rewrite it as 4 root 7 over 7. And this is the answer that I ultimately want to see by the end of this mod. I want you to be able to rationalize. So I would highly encourage to start practicing that now. If you were to leave this on assessments, I wouldn't count anything off. But I would kind of mark on there or just kind of remind you about rationalizing and attempting to rationalize it to get to that final solution. So go through and try rationalizing cotangent. So what would 3 over root 7 look like? I'll kind of pause. Feel free to pause the video. Okay, so 3 over root 7, we can pretty much follow it to a T in the previous problem. Multiply top and bottom by radical 7, so I get 3 root 7 over 7, and that's what the final answer for cotangent should look like here. All right, and so that's the new 3 trig functions. Let me know if you have any questions. Take a look at the practice problems that I have attached here. And it's really just kind of going through and practicing. Hopefully it's pretty straightforward. Most of the work is really just going to come from having to do Pythagorean. You're going to see a lot of problems where you're missing a side and rationalizing other than memorizing, which is which. But go through, use flashcards, use whatever you need to go through and do that. The last part of this video, we're going to look at special right triangles, specifically 2 different things. One, where do they come from? So how are they constructed? And then 2, I want to look at the big 3 trig ratios for these because they're right triangles. Want to look at some special relationships between sine, cosine, and tangent, and essentially look at, again, for these specific ones. And so I want to start by constructing an equilateral triangle. 2, 3, 4. See, I think that's 6, right? 1, 2, 3, 4, 5, 6. Yeah. All right. There's the bottom. So let's just say this is the top. All right. And so let's start with an equilateral triangle here. Equilateral. Can't spell. Triangle. Now, by definition, equilateral triangles have equal sides and angles. And so they're very unique and very special figures and shapes. And if they're all equal sides, then if I let this side here be n, then that means every side has to be n if we were to measure it. The angles are always going to be fixed. All three angles have to add up to give me 180 because I'm supposed to have equal angles. Then 180 divided by 3 is 60. So all angles in an equilateral are 60 degrees. And so this is an equilateral triangle that has a side n, or sides n. And what I'm going to do with this is notice that it's not a right triangle, so I need to create a right triangle out of this. And how I'm going to do that is by taking an equilateral, and I'm literally going to cut it in half. And when I do that, notice that I'm essentially creating this right triangle. I'm going to specifically look at the left half. I'm really creating two right triangles, but I want to focus here. And what I'm going to do is I'm going to take this one and let's bring it out so we can actually look at it. So I'm going to put it right here. So I have this right triangle now where this angle is 90 degrees. This angle is 60. Well, that means that this angle up here in the top has to be 30. And I know that because all three angles have to be 180, but I also know that based on the construction. Remember what I did is I took this equilateral and I cut it in half. I'm literally bisecting this angle, 60 divided by 2. Now, also what I'm doing is remember that this original bottom side here was n, but this side is cutting it in half. So what is this side? N over 2. I know the hypotenuse is n. I'm not changing that diagonal. So the question now becomes, what is the missing side here for this triangle? And that's where this problem gets a little bit difficult in going through and solving for. And so I'm going to walk you through that process. Try it, see if you can go through and find it. So I'll kind of pause here, and then I'll go through and do my work, and feel free to pause it at each step if you need it, or watch it continuously. All right, so to find the missing side here for this 30, 60, 90, I'm going to use Pythagorean. I told you this is going to come up a lot. Pythagorean, again, is a squared plus b squared is equal to c squared. I'm going to let my a be n over 2. My b is going to be the missing side. My c has to be n because that's the hypotenuse. And now I'm going to go through and plug this stuff in. So my a is n over 2, squaring this, plus b, which I don't know, and c, which is n. And so I need to solve this equation for b. All right, so n over 2 squared. Well, this is n over 2 times n over 2. So I get n squared over 4 plus b squared is equal to n squared. Now to help me with this next part, if I'm solving for b squared, I need to subtract the n squared over 4 over. So I get b squared is equal to n squared minus n squared over 4. And I want to show you kind of two different ways to kind of look at this and kind of deal with it. One is that I'm really going through and trying to solve this subtraction problem with fractions. I have n squared over an understood 1 minus n squared over 4. And if I'm going to simplify that or do that subtraction, I need to have a common denominator between these two fractions. To get that common denominator, I need to multiply top and bottom by 4. And so I'm doing 4n squared over 4 minus n squared over 4. 4n squared minus n squared is 3n squared over 4. And so this problem simplifies to b squared is equal to this. Now this is just one approach. Another approach that I want you to kind of see from this, and hopefully this makes sense, is again, I kind of want to go back to the beginning part. B squared is equal to n squared minus n squared over 4. And it really involves like understanding what this fraction means right here. Because I'm essentially saying I have 1 n squared, and I want to subtract from it a quarter of n squared. Notice that this is essentially saying 1/4 of n squared. And so I'm really going through and saying much like we did a second ago, I have 1 and I want to take away a fourth. What's left? Well, that's 3/4 of n squared. And if you compare this with what we got here, it's the same. It's the same approach. It's the same kind of problem. So it's just kind of another way to kind of think about it. So I'm to this part, 3, I'll write it like we had the first time. I need to take the square root. When I take a square root, I'm going to square root every individual thing here because that's all being multiplied and divided. So square root of 3, square root of n squared, square root of 4. I can simplify square root of n squared and square root of 4 as n root 3 over 2. I can't take the square root of 3, so it just stays in the radical, but this is my simplified version. And so we have then, for a special 30, 60, 90 triangle, we now know that the sides always follow this pattern. I'm going to fix this so it looks a little bit more 30, 60, 90-ish. If this is my right angle, my hypotenuse is n. If this is 60, this is 30. Then this is n divided by 2. This is n root 3 over 2. And the n just represents, again, any kind of scaling you want to do and work with. The next triangle that I want to look at is the 45, 45, 90. And the way that it's constructed is by taking a square. So again, just like before, we actually don't even start with a right triangle. I'm going to take a square that's specifically an n by n. So 3, 4, 5, let's go there. 1, 2, 3, 4, 5. Just kind of using the grids to help create my square. So here's an n by n square. We know that by definition, all of these have right angles. So to create a triangle, what I'm going to do is cut along the main diagonal of this square. And when I do that, by taking one of these slices, almost like a grilled cheese, I have a new right triangle that we can look at where this side is n and this side is n. And so I'm going to take this triangle and pull it out so we can focus on just it. And like before, when we were doing the 30, 60, 90, notice that I cut the 90 degrees in these corners by half. That's where the 45, 45, 90 comes from. I'm also missing the hypotenuse here, so I need to go through and find it. So what is C? So I'm going to use the Pythagorean for that. And so I kind of want to give you a second, go through and see if you can find the hypotenuse. Okay, so again, I'm going to use Pythagorean theorem to find the missing side. A squared plus b squared is c squared. Let's just call this side A, this side B. So then this is n squared plus n squared is equal to c squared. And I get 2 n squared is equal to c squared. Now again, I'm solving for c. I'm not solving for n. So this is where I'm going to take the square root of both sides. And again, take the square root of these pieces individually. I can't square root 2, but I can square root n squared. And so I'll get c is n root 2. We put the n out front. There's my missing hypotenuse. So definitely a little bit easier than 30, 60, 90. And root 2. All right, and so that kind of finishes our special triangles. We've got 30, 60, 90. N over 2, and root 3 over 2, n. And then I have a 45, 45. In in root 2. And now your task, what I want you to go through and do is I want you to find the big 3 trigonometric ratios for the following angles. Theta is 30 degrees, theta is 45, and theta is 60. Essentially looking at the respective triangles, go through and find sine of each angle, cosine of each angle, and tangent of each angle. Remember to rationalize if needed, but go through and do that. I will put some work up in a minute, but pause this here, practice going through and finding these 3, and it's going to establish some specific things that we'll talk about and close with. Let's start with theta is equal to 30. So that means my focus is going to be right here in a 30, 60, 90. And I want to go through and find the big 3. So I want to know what is sine of 30 degrees, what is cosine of 30 degrees, and what is tangent of 30 degrees here. All right, now sine again is opposite over hypotenuse. So I'm going to go through and set up that fraction. So 30 degrees, my opposite would be n over 2. My hypotenuse is over n. And then I need to simplify this. Now, the way that we're going to simplify this, and one of the, I pause because I'm trying to figure out the best way to kind of talk about it, is one, these ends will cancel. Like this end and this end will cancel out. There's one up top and one on the bottom. I feel like that's not good enough to help show you why. And so to help show you why, first thing is remember that this n on the denominator is understood as n over 1. And so notice that I'm really kind of doing a fraction divided by another fraction. So we can incorporate our keep, change, flip. So keep n over 2, change it, and flip it. And this kind of gives you a better sense that the n's will cancel because I have an n up top and an n on the bottom, so they'll negate each other. And when then I multiply these out, I get 1/2. So sine of 30 degrees is 1/2. Cosine of 30 is adjacent over hypotenuse. And again, this is going to actually create a very, very similar scenario. So 30 degrees, my adjacent is n root 3 over 2. I'm going to divide this by the hypotenuse, which is n. Again, notice, just like before, we've got fractions. So I'm going to think about this n as n over 1. And then I'm going to rewrite it. Keep, change, flip. Again, notice the n's are going to cancel. My answer is root 3 over 2 for cosine. Tangent, very, very similar. Opposite over adjacent. Opposite is n over 2. I'm dividing this by n root 3 over 2. Keep, change, flip. The n's will cancel. The 2's will cancel. So I get tangent is 1 over root 3. Notice I need to radicalize this. So multiply top and bottom by root 3. And I get root 3 over 3. That's tangent of 30 degrees. So I have sine, cosine, and tangent for 30. And the results here are really, really important. That notice that in all of my answers, none of them contain an n. My question is why? Why is there no n? Well, take a look. Right, and my triangle, notice that what does each side have? So if each sine, cosine, and tangent is all about setting up a division problem, some kind of ratio between one side and another, if every side has an n in it, those n's will always eliminate. So it doesn't matter what the scale is. If you have a 30, 60, 90, and you do sine of 30, sine is always going to be 1/2. It doesn't matter how big that triangle is or how small it is. It's the same thing for 45. We're going to see that in a minute when we go through and do it. It doesn't matter what the n is, the n's are going to cancel. And so if that's the case, then why not take n out? Well, I can't let n be equal to 0. That wouldn't make any sense, right? If n is 0, then this side would be nothing, and I don't have a triangle. And by this side, I mean this one right here. This side would also be 0. It doesn't make any sense. So the next best number is, instead of 0, let's let n be equal to 1. So I'm going to go through and I'm going to change this to make my triangles simpler by letting n just be equal to 1. So I'm going to erase, erase, erase. N is 1, 1, 1. N is 1, 1, 1. And I'm going to go through and continue to find the next 3. So theta is 45 degrees. I want to find sine of 45, cosine of 45, and tangent of 45 for my triangles. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So for sine, because I'm finding sine of 45, that means I'm going to look at my 45, 45, 90 triangle. So I'm going to look right here. And because there are two 45 degrees, it doesn't matter which one I pick, but I need to pick one of them. So I'm going to pick the one in the lower left. Sine is opposite over hypotenuse. Notice without the ends, our lives get a little bit easier. This will be 1 over root 2, which I can rationalize as root 2 over 2. There's sine of 45. Cosine of 45, adjacent over hypotenuse. The adjacent side is 1. Hypotenuse is root 2. Notice how similar this is. It's the exact same, which means the answer is the exact same. Cosine of 45 is also root 2 over 2. Tangent is the dream, because opposite is 1, adjacent is 1, tangent of 45 is just 1. It's very straightforward. Very, very nice. All right, and that leaves us with one last angle, 60 degrees. What is sine of 60? What is cosine of 60? And what is tangent of 60? All right, sine of 60 is opposite over hypotenuse. Since I'm doing 60 degrees, I'm going to go back to my 30, 60, 90. My 60 is in the lower left. Sine is opposite over hypotenuse. So it is root 3 over 2 divided by 1. Notice I'm dividing by 1. So the answer is root 3 over 2. Cosine of 60 is adjacent over hypotenuse, which is 1/2 divided by 1. Again, dividing by 1. The answer is just 1/2. So by simplifying n is equal to 1, it actually really makes our 30, 60, 90 triangles much easier to deal with, because if n is 1, if you go back to our work here, this denominator is 1. This denominator is 1. We don't have to keep change flip every single time. It's very, very nice. The only time that we would actually have to keep change flip is when we do tangent, because this is going to be opposite over adjacent. It's root 3 over 2 divided by 1/2. We have to do keep change flip here. And we would get root 3 over 2, change flip, 1/2s cancel, or 1/2s, the 2's cancel. And I'm left with radical 3 over 1, which is just radical 3. Notice I don't have to rationalize this. We're actually done with that. So here's sine, cosine, and tangent for The three special angles, notice we didn't do 90. We'll talk about that one later. And so this is how the special right triangles are used, and these are the ratios here. Again, the important properties to see here, and this is kind of the closure for this video, is notice that the scale of the right triangle doesn't matter. Sine of 30 is always 1/2, always. Doesn't matter how big your triangle is. The second thing that I want you to see from this is that we just looked at 30 degrees, 45 degrees, and 60 degrees. Well, 30 degrees is a degree measure. Remember, we want to measure in radians and look at things in radians. Well, 30 degrees in radians is pi over 6. 45 is pi over 4. And 60 degrees is pi over 3. So if I asked you to find, say, cosine of pi over 4, what I'm asking you to do is find cosine of 45 degrees. I'm telling you to go to a 45, 45, 90 triangle and find the adjacent over hypotenuse. We've done that. The answer is root 2 over 2. And so it doesn't matter whether we're starting in radians or degrees, we're still looking at these special ones. And that's why these are so important. And we know that this is connected with the circle because these are the marks of the circle that we put on there, this over 6, over 4, and over 3. And so we can actually go through now and you can kind of relabel what we found was the big 3 for not only 30 degrees, but also pi over 6. We found the big 3 not only for 45 degrees, but for pi over 4. And not only for 60, but for pi over 3. The last thing that I want to point out is that sine, cosine, and tangent right now are limited to right triangles. And if you remember from the first part of the video, if you watch the first part, the angle that we're taking sine, cosine, and tangent of, that we're trying to find the ratio of, is stuck between 0 and 90 degrees. In other words, I'm limited to what I can find sine, cosine, and tangent of. I can't go past 90. And we know from the unit circle that this is in the first quadrant, right? 0 to 90 runs from here to here. But we know that angles can go past this, right? We know that angles can be in quadrant 2, quadrant 3, or even quadrant 4. So how do I find sine, cosine, and tangent? How do I find cosecant, secant, and cotangent when my angles are greater than 90 degrees? What do we do with that? And so that's what we'll do in the next video, is to kind of go through and start digging into how do we answer this question? And it stems from everything we've done today. So this is kind of the foundation for digging into and finding sine, cosine, and tangent for angles that are greater than 90. What if I don't have a right triangle? How can I find sine, cosine, and tangent and look at that? And so that's it. So take a look at the practice problems. Let me know if you have any questions, and feel free to move on to the next video when it's up.